It's also not. So here's why I mentioned the thing about vertex. How many points do I already have for both graphs? For each function, I already have how many points? These are the points where the two functions do what? Intersect. So those 2 points work for both functions. I already have 2 points for both functions. The only other point is the most important point for a parabola is the vertex. If I can get the vertex for each parabola, I can get a nice, really nice sketch for both. That's why I gave you a little room here. How do I find the vertex for this guy? What's the shortcut? You could take the derivative, set equals 0, or you can remember the shortcut from pre-calc. What was the shortcut? Negative b over 2a. So it would be 12 divided by 4, so y is 3. If you take the derivative, you get 4y minus 12, set that equal to 0, y is 3. Get the same thing. So this vertex is at... Somebody still with me? You guys get the idea? I mean, it's... So when y is 3, x is going to be 18 minus negative 18. It looks like x is 1. So that's the vertex for that guy. What's the vertex for this guy going to be? Negative 6 over twice negative 1, so also 3. So his vertex is going to be, when y is 3, you get negative 9 plus 18 is 9. Is that 13? Did I make enough? Oh, okay. Poor guy. Is that 13? Yeah, I did. Oh, yeah, that's x. Okay. I was hoping I gave you enough scale to work with. So if I want to plot this guy, his vertex is at 1, 3. So about right here. And then he goes to the points 9, 5, and 9, 1. So here's this guy. Let's see how bad I can angle this guy. Pretty bad. Okay, make that big. All right, there's that guy. He's got the one black eye. Poor little dude. And then this guy, he goes through those points also, but his vertex is 13, 3. And then he's just going to go through those whole same points. Okay, so I saw a lot of that picture. Unfortunately, I saw a lot of that on calculators too, so I should be able to do that by hand. So I want this area here. Now, I really... Do I have the option of doing dx? If I want to do integral dx, I have to be able to get my functions I'm working with as functions of x. So they match with dx. Can anybody solve either one of those for y easily? Can you solve that for y? Can you? Look at it. Can you get y by itself? Is it possible? It sort of is, but it's disgusting as all hell. You have to do a variation of quadratic, and oh my God, you don't want to do it. So no, I'd rather keep it like that. That's a nice polynomial. I don't want to mess with that. All right? I don't want any weird radicals showing up in this if I don't need them. So therefore, and listen, you guys with me here? I mean, this is the function I'm working with cannot at all easily be solved as a function of x. So I've got to give up on integral dx. I've got to do integral dy. And the minute I figure that first step out, it tells me how to do everything else. So what is y doing on that interval? This is going to be a little bit weird maybe, but what is y going from to? So it's easy to see what x is doing. Let me start there. X is going from this wall up to that wall, right? What's this guy? What's the upper wall? What's this guy? What's this side? What's the upper wall? Who's this guy? It's got to be the one that's going backwards, so it's got to be the one that's negative, right? So this wall is negative y squared plus 6y plus 4. What's this wall here? That's the other one. 2y squared minus 12y plus 19. So I know that x is going from this up to this. You didn't give yourself enough room, Jeff. Well, that's too damn bad. So it'll be negative y squared plus 6y plus 4. That's the top one. Minus 2y squared minus 12y plus 19. And let me be really overly explanatory. If I drew a rectangle in, how tall is that rectangle? If I do it like this, how tall is it? It's going to be this side minus that side. That's going to be the height. This minus that is the height of each rectangle. Now, for every rectangle I can draw, what's the y starting and going to? The y starts at this and it goes up to this. And we already know what those are. This is y equal to 1. And this is y equal to 5. That's where they meet. From 1 to 5. That's what y is doing. Y is going from 1 to 5. So how do I scan this region? Here's another way. We do it over here. So that's one. Come down a little bit. Here. All right, Jeff. It's okay. There you go, buddy. My little submarine here. I like it. So as I go from 1 to 5 on the y, as my little dude walks, what's the function doing? It's going from this wall to that wall. Move up a little bit. Now it's going between those two. Move up. Now it's going still between those two same walls. So as I move from 1 to 5 on the y-axis, what's happening in the x direction is going between this wall and that wall. So this is what this says. As y changes from 1 to 5, what does x do? It goes between this wall and that wall. And now you've got a relatively easy integral to do. All right, so go ahead and finish that part up. Yes?
How do you know that the y squared wall, the negative y squared wall comes first?
Because he's the one that's on top. And again, what does top mean in this case? Well, if I'm going dy, now I'm like this. That's why I'm drawing my rectangle. So how long, if you want to keep it in terms of how long it is, if you want to think about it that way, how long is that rectangle?
I'm just wondering in this example why it's considered on top, because it's kind of even to me. I'm just wondering why.
Even? So
well, I mean,
pick a y between 1 and 5. So like this y right here, just to pick one. Which one is further away from that? Here or there? Which one is further away?
Oh,
this
you're saying to kind of look at it sideways.
Yes, that's why I keep doing this in my head, right? Right?
Yeah.
So now I'm considering this to be my base. We've always considered x to be the base, but this is an example of how you can certainly look at it the other way. Either your function is in a form you can't solve for the letter you wish, or you can, but the integral is impossible to do. So we're just making what we can do more general. We're saying, we didn't used to be able to do this integral at all, but now we did, because we shifted our perspective. In general, x and y are completely arbitrary. How you put a coordinate system down on something is completely up to you. There will be an easier way to do it and a harder way almost all the time. So now this is the easy step. It always kind of sucks when one of the limits isn't 0. You're like, oh man, oh well. So now it's just going to be plug a 5 in. Minus plug a 1 in. And whatever all that business comes out to be. Just to show you a little weird little place, that little thing I talked about earlier. Look at this. And again, I know this isn't very impressive if you're somebody that only uses a calculator. 125 is 5 times 25. So negative 5 25s plus 9 25s is 4 25s is 100. I don't need no freaking calculator. Negative, isn't 125 negative 5 25s? Right? 5 times 25 is 125. Are you guys with me? Are you guys with me? Okay. Plus 9 25s. Well, what's negative 5 25s plus 9 25s? 4 25s, which is 100. If it works for variables, it has to work for numbers because variables are freaking numbers. So what's negative 5x plus 9x? 4x. X is 25. That's 100. And again, I know some of you guys are like, Jeff, you remember they invented this thing? I don't give a shit. The more you understand this kind of stuff, the more connections you can make about other things. And we are so far removed from this, we're unable to make all the connections we're supposed to. All right. And then 15 times 5 is 75. So I get 25 from this minus 8 minus 15 negative 7. I get 32. Is that right? Let's see if I did that too fast. I don't know. Anybody do that? Yes? Is that what you got? Yes. Okay. Thank you. Please help me out. Okay. If you get a negative answer for this kind of problem, because this is supposed to be a true physical area, what that normally means is you put the wrong function first. You did floor minus ceiling. That'll be a negative height then. It's got to be ceiling minus floor. Okay. Oh shit. So many new things in one problem. Any questions? You guys all right? Sorry. And that last little bit I did with the 5 and the 9 and shit, don't worry. I mean, if you don't like that, don't. It's all right. I'll let it go. It's just a cool little thing. And you should be making more of those cool little things for yourself. You make math your own thing. Mathematics needs new ideas, always. Well, we need more people in it. Okay. So this section 6.1 adds a little bit of algebra on top, but it basically boils down to an integral problem. And as long as the function on the inside is not too funkadelic, it shouldn't be that hard once you get the integral set up. The new stuff is this idea of first figuring out, do I want integral dy or integral dx? We never knew that was an option before. And now we do. And in this case, I definitely want to do integral dy because it would be unbelievably difficult and disgusting to solve this to be a function of x instead. That would so desperately suck. Okay? So, here's what we're about to get into. I believe that's all 619. Yeah, I like it. Sweet. So, here's what I was talking about, a visual aid to help me out. So, do me a favor. Can you sketch the graph? Sketch this graph for me. For this function here. Shit, where am I? I need to hope to God somebody notices what that is geometrically. But even if you don't, you should be able to sketch that graph. Just plug in some numbers in. Good. I see a lot of people just staring ahead. Do it. Sketch that graph. If you don't want to sketch it, draw a little duck. I'll think you're doing something. Did anybody know what this should look like before you started graphing it? Anybody? Because this is y equals square root of 1 minus x squared. If you square both sides, add x squared over, you get that. And that's the graph of what? Circle. But the fact that this is the positive root means it's going to be the upper part, so it should look like that. That is just something you really should just know. But if you don't, you can still plug points in and get it. No big deal. So you should have gotten this. The curvature kind of sucks them, or scales bad. Yes? Say again, sorry. Oh, please. Don't do that to me. I don't mean to. So I'm not calling you out. You just happen to be the poor person that tried to do that. Everybody, this is the first thing I talk to with my colleagues. I'm sorry, you just stepped into this a little bit. What is this? If somebody writes this, what would you tell them? Or if that's what you thought it was, keep it to yourself. Don't want to know. Sad enough already. What would you tell somebody that did this? What did they do that's not legal? What did they do? Yeah, distributed the square. That doesn't make any damn sense. What are exponents based on? What operation? What operation are exponents based on? Multiplication. And what's inside? So they're not going to play well with each other. So why can it distribute a 2 in front of this? Because coefficients are based on addition. That's why. It'll play well with addition and subtraction. Because there really is no subtraction. There's just adding the inverse. So there's this. So of course it's going to be able to distribute easy. Bless you. Is this true? Now I might have scared you guys, but I mean, is that true? Of course it is, because what's happening inside? Multiplication, which is what this guy is based on. So of course it's going to be easy. Of course they're going to play well together. So what would you tell this person? This is a person in like Math 90 What would you suggest they do to not make this mistake? What does it mean to square something? You write it twice. So what am I missing? I'm missing the middle piece. And so so if I have this is not equal to this for the exact same reason. Right? This is not equal to, just in case you wrote that down in your notes. You're like, my teacher said this. No, stop it. It's not equal to. Right? Same reason, because how do we rewrite square root of a plus b to the 1/2? Still can't distribute. It's still a power. So roots are powers. They're fractional powers. When I teach this, I try to tell my students, I wish we had never come up with this stupid symbol, to be completely honest. It's totally unnecessary. We could just do always fractional exponents. Much more useful way to represent it. And in this case, you understand then that roots follow the same rules that powers do. They can't distribute across addition, subtraction. So I can't say this is 1 minus x, because the square root can't distribute across the minus. Is that, you guys with me? If you're not careful, you're going to be like, oh, that homework was easy because all your radicals became not radicals and it was easy. Well, it's not legal. Stop it. Okay. I like it. Maybe. So anyway, I'm sorry. I'm not coming down on you. It's a beautiful time to bring that up, because this is about the time it's going to start to happen a lot. So you got to be careful. Don't be overly optimistic. Okay. Now, here's the cool thing. This is where I did the visual aid. If I were to rotate that shape around the x-axis, so I'm going to rotate it around the x-axis. So like this. A few years back, a student got me this after I described it. These little ornaments, you ever seen these? So there's the shape, right? It's a lot better circle. My curves are wrong, but oh well. So if I rotate it around, of course it's going to make what shape? Sphere. I like it, right? Ooh, Jeff. All right, give me a break. It's still a nice visual aid. So you're not going to have to draw 3D in these sections. Let's first develop a way. So if I wanted to find the volume of the sphere that I get by rotating this. So I'm going to draw, it's going to be a football, but oh well, it's going to be Stewie's head. It's too bad. Right? It's supposed to be circle, but too bad. My scale's bad. So this is a sphere. Let me put the little requisite little shiny point on it. It's a nice sphere. We're going to kind of prove the volume of a sphere formula right now. Right? So I know some of you guys might remember what the formula is. We're going to prove it. One way to do this is if I slice the sphere this way, what shapes am I making? If I take a section, if I chop it, and then I look at it, what shape did I just make? What shape will that cross section be in? Circle, right? So if I chop it like right here, some x value, it's going to be, let me see if I can do this. That's really good for me. I think it should be the other way. Jeff, oh well. It was almost good. You guys get the idea? I'm kind of overstating it a bit, but still. Chop, and I get that circle. I could do that at every x value. And how many x value are there? An infinite number. That's why I'm going to eventually do an integral. What am I going to do? What can I do right now with that circle? I could figure out its area. And then if I could get every single possible circle and add all their areas, I will end up with the volume of the sphere. Let that kind of sink in. It's kind of almost too nifty to believe. Let me try this again. If I chop this circle with an unbelievably sharp blade, like an atom level blade sharpness, so I can cut it at every single x value. So I'm going to make an infinite number of cuts. I am the infinite chef. All right, so chop. I might be Swedish, I don't know. Chop. And then I add up all those areas of every slice I took, I will end up with what the volume of the thing was. So what's beautiful to me about this is so beautiful to me. When I first learned this, I hated this shit, just to let you in on something, because my teacher sucked so bad. But then eventually I was like, oh, that's so freaking cool. We're going to set up an integral that will represent a three-dimensional idea, but it's not going to be nearly that hard looking. I mean, it's kind of cool that we can represent a three-dimensional idea with what looks like a one-dimensional thing. What is the area of that circle I just drew? What's the radius of that circle? Let's start there. What's the radius of that circle? You can do it. Come on. What's the radius of that circle? It should be kind of right on the heels of what we just did, right? What's the center goes through 0, and how far do I have to go until I hit the edge of that circle? That. The function is the radius of the circle, isn't it? Do you guys see that? Just like the function is the height of the rectangle, right? Same idea kind of carries over here. So what is the area of this circle going to be? Well, so it's pi r squared, right? So it's going to be pi times, get out of there, the square root of 1 minus x squared, squared. That's really nice. That's the area. Now look what I did. I could have drawn that little circle anywhere. And then the representation of its area would have been the same damn thing. So I just pick an arbitrary place to put a circle so I can look at it, and I understand that it carries throughout. I could have put it anywhere. So now, of course, what does that become? It's almost too nice to believe, right? It just becomes pi times this. Yay! And then how do I end up getting the volume of the sphere then? Is I just add up all those circles. I can't use the sum symbol because how many circles are there? Infinite number. So I'm going to add up an infinite number of, okay, so that means integrate these. And what is x doing? Going from what to what? X is going from -1 to 1. I like it. I can see that. The x is going from -1 to 1. So they're going to give you a region, you're going to draw it, and they're going to say, now rotate it around this axis. So when you draw the region, you know what your variables are doing. You know where they're going from to. Are you going to sometimes have to do y? Yeah, that's the whole thing. That's going to come in too. So it's going from -1 to 1. So if I chop, and then get the areas of those circles, add up all the areas of circles from -1 to 1. Let's see what we get. I can take the pi out of there because it's a constant. That's always nice to do. Let me see if you guys can handle this right now. Let me see. Well, let's see. I told you I was going to do this sometimes. I don't have to do what I'm about to do, but I want to show you so it gets you thinking about this. Would there be any difference on either side of this? Would the answer I get for this bit be different from this bit? In terms of volume, or even air, sure, yeah. No, right? Because this is cutting it in half, isn't it? It's symmetric to the y-axis. Let me see if you guys, if you don't get this right now, we're not to the point where you have to get it yet. Right? So watch this. What does that mean? If I do the integral from 0 to 1, if I do this, that is how related to the answer. That's only how much of it? So I got to double it. That's too nice. So if it's symmetric to the axis, you can go from 0 to that and double it. If you're not sure if it really is symmetric, don't do it. Because you really don't have to. But you see why I would want to? I got a 0 now. I've got a polynomial. When I do my limits, I don't have to worry about half of it. Right? And again, it's not that huge of a shortcut, but there are areas where you almost have to do this to at least make it a lot easier. This is not really making it a ton easier. So let's see, what do we get? We get 2 pi x minus x cubed over 3. And now I really just have to worry about putting a 1 in. Is that cool? Because 0, of course, will make that all 0. So now I get 2 pi times 1 minus 1/3. And 1 minus 1/3 is 2/3. And 2/3 times 2 pi is 4/3 pi. So sure enough, what's the volume formula for a sphere? Does anybody remember? 4/3 pi r cubed. So for radius 1, it would be 4/3 pi times 1 cubed, 4/3 pi. And what I'm used to is the crowd goes, eh. Okay. There's so much cool shit in this. This work, do you see what I mean by this work looks one-dimensional? It's all dealing with x. We understand that y is what this results in, but this work looks one-dimensional. But what is it representing? A three-dimensional idea. That's so cool. Why? Because when I'm doing this integral, what I'm adding up are actually areas, and when I add them all up, I end up with a volume. Right? It's that idea of what's the volume of a cylinder? Does anybody remember? There's a nice way to get it. You ready? What's the area of the base? What's the area of the base? It's a circle, so it's pi r squared. Right? Nobody wants to say it. And how many do I have them stacked up? This many. There you go. So it's h pi r squares. So beautiful of an idea. Any repeated shape like that, the volume of it will be the area of the shape times the height, or if it's laying down, the length, right? So if I had a prism like a triangular prism, like a little pup tent, what's its volume going to be? The area of this times the length. Because it's that shape repeated. Maybe that's Toblerone. Shit, now I want some Toblerone. If you don't know Toblerone, I'm sorry. Your life is incomplete. Okay. That's all some side notes. So let me do this. So we're going to sort of do like we did with this. We're going to kind of piece this thing together. Remarkably enough, I have another sheet, but we're going to kind of do this one together. Now this method we're using right now is called the disk method. If you look at, now be careful. I handed them out in a certain way because I don't want you to excessively freak out. If you want to look at this side, feel free. All right. I put this together a while back. I like it, but I don't know how you guys are going to feel about it. So what I will point out one thing. This is what we're doing right now. These are called the method of disks. Don't worry about this other shit yet. The method of disks. Because here's my circle, and then the dx is kind of like the width. So that's why it's called the disk method. But I still am. See, there's the idea. And so what's beautiful about this, here's the piece I need to really make sure you understand. I don't have to just have a part of a circle for this to work. If I have some general shape, some function like this, wow, and I rotate it, I'm going to get some funky ass looking vase thing, right? You guys kind of with me? Or goblet? Well, let's see if I can handle this. This is the part you don't have to do. Thank God. All right, that's not too bad. I could do a lot worse. So it's not like a nice part of a circle, but who gives a shit? If I slice it the exact same way we did this, if I slice it somewhere, I'm still going to make a circle. So I can integrate from 0 to whatever the shit that is. What's the radius going to be for every circle? F of x. Why is the radius easy for this one? I want to point this out because we're about to do some where the radius won't be quite as immediate because it's rotating around the 0 line, right? If I rotate around something off axis, the radius might get a little longer or shorter. So if I rotate around this line instead, the radius would be longer by 1. The radius would be f of x plus 1. I made the radius a little bit longer. Does that semi-make some sense? Okay. So the idea that we developed for a beautiful spherical shape doesn't matter what the shape of the thing is that I'm going to rotate. I can still use that same idea because every time I take a slice, it's circle. Because why? Why does it make sense? Because I'm rotating it. So I am making all these circles as I rotate it. So let's look at this side. So what I want us to do for this side, let's do this one together. Look at these. We're going to do these two first. And you can see how I'm starting to do it around other lines, not the x-axis or something. So let's sketch this region. Take a minute and just sketch that region. That's exactly like we were doing before. I think we did that same exact region earlier. Sketch that region on that graph. Is that cool? Just that region right there? It's not that bad. Right? Y equals 0 is the x-axis and so forth. Let me say this right now. The radius is always, the situation is always easier when my region is hugging my axis. So right now, is my region hugging the axis I'm rotating around? Yes. So there's going to be an element that's easier for this problem. We're going to see a problem in a minute that's not true, and I'll show you what we have to do. So I'm going to rotate this region so you don't have to draw the 3D part, thank God. Unless you're a really good artist, and then you can do it just so you can make me be all jealous. But just for the sake of something to look at, if I did try to do this, it would look like that, right? Did it really lightly because I was uncertain about what I was doing. Okay. You guys semi with me? So you rotate this sucker around the x-axis. You're going to end up with this really funky, hopefully it's not like a glass, because if you put it down, it's like going to fall all over. So maybe that's a funky hat. I don't know. You guys with me? No? Is everybody all right? Okay. So how do I go about this? So here's the general idea. The general idea is going to be this. That's what it is right now. The radius could become something worse. But right now it's easy because I'm going around the x-axis. There's no funky other stuff. So pi times the radius squared. So what's the radius going to be in this case? It's going to be the function value. That's how far away I get from the center. So what is the radius for any circle? The distance from the center. The center is going to be what I'm rotating around. And then I just have to see how far away is the function away from that. That's the radius. And so the idea this is built on is unbelievably simple. Pi r squared, add them up. That's all the idea is. We're going to mess with that idea a little bit because we're going to have, what if it wasn't the x-axis? What if it was away from it a little bit or something? Or what if there were two functions and I want to rotate the region between two functions around and get some really weird shit going? We're going to do one of those in a minute. So to set this up, why is this dx? Why did I choose dx? And I'll tell you exactly why. It's not because the function is nice already. It's because how do I locate my circles? I really want this to make sense. How do I locate my circles? Since I'm rotating around the x-axis, I locate them on the x-axis. So where's that circle? It's at 2. There's a circle there. So at this x value, there's a circle there. Are you guys seeing that? Because we're going to learn a different method. The other method works when this method doesn't work. That's almost too nice to believe. But the other method is going to involve a different idea. It's going to be integral dy when this guy wants to be integral dx. So it's going to save our ass if that way would be easier. So inside, I'm going to put, how big is this radius? It's x squared. And then I square it because it's pi r squared is the idea of the area of the circles. And what's x doing? What's x going from to? Yeah, it's going from 0 to 2. And sometimes you'll see that in the region setup. Right? When y is 0, x is 0. And then x goes up to 2. So x goes from 0 to 2. You can see it from the picture. That's the better place to get it. And now that's a really easy integral. I have no qualms saying that. Go ahead and do that real quick. Figure out that integral. All right, is that all right? And then, of course, you plug a 0 and it's not going to get in. So it only depends on what 2. So you get 32 pi over 5. I like it. So that part is easy. It's the setting the integral up part that's difficult. That part should be easy. So what's the only difference between what we just did in this one? Still got the y equals x squared, but now I have a different floor. I have a different... But what am I'm still rotating around the x-axis. So if I graph these... Now, of course, where do these two meet? I have to figure that out first. I want to rotate the region described by these around the x-axis. So where do these two meet? I would hope maybe you could just see that by looking at it. Yeah, they meet at 2, and of course, the trivial solution is 0. So they meet at 0 and 2. So now I've got this shape like I had before in the first one, but I don't want to rotate the region beneath it around. I want to rotate this banana region around. Because here's y equals 2x, right? So what is important in this method is to figure out what the radius is and then to figure out what the region is I'm rotating. So now watch this. If I calculated the volume by just rotating this line around, this is a three-dimensional cookie cutter problem. So the one we just did was the inside volume. If I rotate this region around, I get that inside volume, right? So if I really want you guys to see this. If I rotate this around by itself, I'm going to get some big volume, right? It's going to be a little bit bigger than the volume I got in the first problem. How do I know that? Because it goes a little further. Because here's the y equals x squared. Right? It goes like that. So what I want to do then is I want to find the volume that this guy makes when I rotate him around and subtract the volume we just got. So it's that same idea of subtracting two functions, really. So here's the problem, though. Let me ask you, let me see if you guys get this. There's an inner radius and an outer radius. So this is why this method is called the washer method. So when I say washer, you guys know what washers look like, right? Hopefully. They look like that. Yay. So it's like I bored the middle out. The same way I bore you guys. No, this is different. So I bored the middle of this thing out. So what that translates into is the same idea as the cookie cutter. I want to take the big volume minus the small volume, and I end up with the volume that this banana shape makes when I rotate it. It's exactly like just finding the area of that banana shape. Same kind of idea. Here's the slight difference. How do I find, this guy, so in general it's going to be pi r squared, but now I want to do pi outer radius squared minus pi inner radius squared, because I want to subtract that inside volume. So I don't want to have, so I want this, so up here, this wouldn't really be a hat because it would be solid, right? Because I rotated this whole region around, so there's no, it would just kind of like balance on my head. It's got a solid bottom to it. This will have, whoops, let me get it all the way around there. An empty middle. It could actually hold stuff in the middle because I'm not rotating this part. I'm just rotating the banana piece. So it could actually hold water if I turned it like this. Some kind of weird bird bath. Maybe. Have you guys ever seen a bundt cake pan? It's got the middle missing. So it's like you find the area of the whole thing, or the volume of the whole thing, minus this, because they've chopped that part out. Okay, I like it. Okay. So what does this translate into then? Well, it translates into this. When I have an empty middle, and this is what I was talking about before, this function, does it hug, this region, does it hug the axis? Yes. Does this region hug the axis? No, that's going to be the washer method, and to be really honest, there's no flippin' washer method. It's the disk method, and this is one where I have two disks and I subtract their volumes, because I'm cutting the middle one out. So don't think that there's disk method and washer is totally different. No, it isn't. It's just two disks, and you subtract the smaller one from the bigger one. That's all it is. So in this case, it's going to be, the bigger one is going to be what we in general call radius outer, because that's the outer radius, kind of makes sense. And this is going to be the inner radius. So what is the outer radius going to be? How long is this? How long is this? What's this? 2x. So the inner radius, the outer radius is 2x. What's the inner radius going to be? X squared. So then what am I going to do? I'm going to take, let me totally write it out too much. I'm going to take pi times this radius squared, and then cut out the middle, minus pi times this radius squared. I don't know why I'm writing all sideways, but too bad. And what's x doing still? X is still going from, what's x going from 0 to 2 still? But to see how this boils down, I can take a pi out, just get the pi the hell out of the way so I don't have to carry it around with me. And now that we got the integral set up, it should be relatively easy to do. They could throw some really funky stuff at us, some secant squares and whatever. Or some u sub even might show up in these. This one's not hard, so you get pi times 4/3 x cubed, become like 3, minus x to the 5th over 5 from 0 to 2. So it just depends on what it is at 2. So 2 cubed is 8 times 4 is 32. So I get 32 pi over 3 minus 2 to the 5th is 32. 32 fifths pi. Why am I doing that? I don't know. Here's what it is. So it's 32 pi over 3 minus 32